So just to demonstrate the chair flip, here notice all the white substituents are axial. They're pointed straight up and down. Green substituents are equatorial. They're around the middle. If I flip one side up and then one side down, I've switched the places of all of them. Greens are now axial. Whites are equatorial. You can pick any two carbons and do the flip, and it'll do that same interchange. And a cyclohexane molecule is doing that thousands and thousands of times a second. All right, back to business. All right, when you're drawing a chair flip, drawing a chair flip requires that you rotate around every bond in the ring at the same time. The axial substituents end up switching with the equatorial substituents. Everything that was pointed up remains pointed up after the chair flip, and everything that was pointed down remains pointed down. It's just the equatorial ones that were slightly angled up are now pointed straight up. The equatorial ones that were slightly angled down are now straight down, and vice versa. The axial ones that were straight up are now angled up. So we don't change whether things are up or down. We only change whether they're axial or equatorial. So here's a drawing of a chair flip for a molecule. All right. Now this molecule, if I were to draw a planar projection of it, would look like this. A planar projection, I would have, I'm going to number my carbons. I'll call this carbon 1 with the OH on it, and then 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. If I were to draw a planar projection, what this would look like is carbon 1 has an OH group. Carbon 3 has a methyl group. And carbon 6 has an ethyl group. So if I start with the conformation on the left, when I do the chair flip, the ethyl group was pointed straight up, remains angled up. The OH group was pointed straight down, it remains angled down. The methyl group was angled up, and now afterwards it's straight up. Yep. So the question is, how do you get this to happen? This just happens on its own. This happens thousands of times a second. Just like rotation around single bonds happens. No, it's not like resonance. So resonance happens with electron sharing among atoms. This is just bond rotation. So just like when we drew Newman projections, and we said we could rotate around the bond and go to different conformations by rotation, this is the same thing. It's just, well, it's bond rotation, which is related to vibration. I mean, it's the constant motion of atoms. Yeah, so this can also be drawn with Newman projections. I don't do it, but in Khan Academy they do. So you can check those videos out. But it's very similar to what we analyze with Newman projections. Yeah, so, I mean, we talked about why chair is more stable, because every bond is staggered, whereas in the boat conformation, some bonds are eclipsed, and actually there's two hydrogen atoms in the middle that really get in each other's face. So it's much less stable. All right, I think I'm going to have to call it a day there, and then next time I'll talk about how to draw the chair flip without even using a model. And just give tips.